I'm very glad to be here in more ways than one. I should have been here yesterday morning, but I was on an Air France flight with a bomb threat on Tuesday afternoon that was diverted to Halifax, Canada, and it took from Tuesday afternoon to last night midnight to arrive here. So I am very happy to be here, but I missed all the wonderful talks yesterday. So this talk seems to like it's going to cover a lot of different topics, but the different topics for me are just synthesized into one simple definition of big data. So let's start with a little definition exam here. Okay, so as mentioned in the opening there, I just joined this firm about 6 months ago. My prior life, 12 years teaching data science at a university. And so I've been missing giving exams to students, so I'll give you an exam today. Okay. And so I'm going to start off with a very simple quiz. And so you don't have to actually answer this or raise your hand, but just be thinking about it. And so it's just to complete this sentence, which is the definition of big data. Okay, so big data is, big data is the new bacon. Big data is the new black. Big data is the new oil. So I know what you're thinking. Kirk, you had me at bacon. But the real definition I want to focus in on is very simple. When people say, what is big data to you? To me, big data is everything quantified and tracked. So when people say we've always had big data, I say you may think you've always had big data, but we have never in the history of humanity put a sensor on everything and tracked everything. All right, so some people claim that ancient Rome had big data because when they did the first census of the world and they collected the census, the population count in all their cities and city-states across their empire, that was a lot more information than they had ever handled before. Okay, so that's one definition of big data that is more than you've previously been able to handle before, and if you look up Wikipedia, that's what they say, but I think that's BS. Big data is the fact that we are now sensing everything, your sentiment on social media. We're putting sensors on our refrigerators, on our devices. We're tracking everything, whether it's in retail marketing or in space or on Earth or in climate or under the oceans or in cybersecurity environments or even in national security environments, even bomb threats on airplanes. We have sensors tracking everything and collecting that data continuously all the time. And to me, that's the generation of big data like we've never, ever seen before. And so if we think that's enormous, wait till the Internet of Things arrives where we truly, absolutely now have sensors on everything. Okay, so this talk is about that sort of idea, the concept of how we sensorize the world and we put a tracer on everything in order to build a model of understanding our world. And whether our world is marketing or astrophysics or climate change or cybersecurity or whatever it happens to be, fintech, whatever your world is, understanding how something, a customer, a user, an asteroid, or whatever moves through that universe that you live in, understanding that is what we're attempting to achieve through our analytics applied to our big data. So hopefully that sort of puts a synthesis on why there's so many different topics listed in this title here. As I always tell my audiences, my background is astrophysics, but I'm not here to give you an astrophysics lesson. I may give you some astrophysics stories, but that's just as a metaphor, as an instructive model as to how this stuff is applied everywhere. So as a background as a scientist, I always like to start off with why are we here? So I always tell people the most important things in data science are the data and the science. Okay. So all too often people say, is Hadoop big data? And I said, no, Hadoop is a technology that enables you to do things with big data, but that is not big data. Data science is about the scientific method as applied to data that we collect. So this is a very human thing. I was having a conversation with someone earlier this morning, and I said we're all born forensic detectives, right? We're all born looking around and seeing what's going on and asking questions about what's going on around us, our world around us. Okay, even as small children, we do that. So ever since we began to explore our world, we've asked questions about the world. Okay, and so the more questions we ask, we see more interesting patterns, we ask more questions. So we have to go out and collect more data to answer those new questions. And as we collect those new data and examine that, we come up with more questions. So we need to go out and collect more data to answer those questions. So if you know anything about the exponential function, people, mathematical backgrounds here? So what's the wonderful property of an exponential function? It's the function whose first derivative is proportional to itself. The rate of change of a function when it's proportional to itself has an exponential growth curve. That's the definition of an exponential function. That's why big data is exploding exponentially, because we collect X amount of data, we can ask so many questions, and we have to go collect a proportional amount more data to answer those new questions. So now we have this much data, and we have to go out and collect a proportionally similar amount of data to answer those questions. And then we have to ask that, go collect a proportional amount to that data to answer the new questions. Okay, so it just grows upon itself in this multiplicative way, which leads to an exponential growth. And so for just a very simple example here, so here's a map on the left. I won't try to use a pointer here, but the hotspot map on the heat map on the left shows the location of crime statistics in San Francisco. All right, so initially, what was behind this was basically an Excel spreadsheet that showed the locations of crimes in San Francisco, particularly car thefts. Okay, so this started out as an Excel spreadsheet. Not a whole lot of insight, just looking at tables of numbers. I'm sure we all agree with that, right? So someone looking at this table of numbers and seeing this list of places where cars were stolen across the city will ask a question, well, can you show me where that happened? So from that set of questioning, something new was generated, which is this geospatial map, this heat map on the left, all right? And so we can drill down into that heat map and start asking specific questions about individual neighborhoods. So we're collecting more data, putting geospatial tags on it in more specific locations, but after people see that, they say, well, is it dependent upon time of day where crimes will happen, where car thefts will happen? And so now we add another dimension. We go out and collect data to get the time dependence, time of day dependence of where this stuff is happening. So the more we see the data, the more questions we want to ask and answers we want to find. And that's how it works, because as humans, we're just naturally inquisitive about our universe, our world, and asking data, collecting data and as evidence to answer those questions is what we do. So naturally, as we all know, so this was supposed to be the keynote yesterday morning, so if this looks introductory to you, some of this I was going to swap out at the last minute, but it's a little hard to completely change all your slides in the 2 minutes before you're supposed to stand up, so I didn't try to do that. Anyway, so we're seeing this exponential growth of data and data opportunities as reflected in the job opportunities, but certainly in a lot of ways we see this in every discipline everywhere. And so this is an eye chart. Don't try to read all of this, but it's my way of sort of summarizing that sort of universe of possibilities of how data analytics, data, and applications of data to our lives is improving and changing everything. Okay, so we're talking about smart apps. Okay, so your smart apps do things like find the next best value, or the best restaurant, or the best place to stay, or something like that, or the best place to go for a beer after the conference. We can do other things. It does other things for us, like it predicts what word to complete as you're typing your text message. Okay, so that autocomplete function, the type ahead function, is useful except when it doesn't work right. And we have no examples of the wrong messages being sent to people because the autocomplete put a wrong word there. But anyway, but it tries to simplify our lives. We have predictive retail, dynamic pricing, smart supply chain, precision demand forecast. So smart retail, precision marketing, that segment of one, giving that precise marketing campaign, that precise offer to each individual user, okay, based upon their preference and their context, their interests and their intents. So around all of that, what I just said is context is the all-important thing. People used to say content is king, and I'm not going to argue with that, but I think context trumps content. That is, knowing sort of the context of someone is way more important than content, okay? So if I'm looking at, I'm sitting in the airport in Halifax for 36 hours waiting for my plane to be cleared so we can fly to Paris, and I go on my Netflix account and they recommend some airline crash movie to me because I like those disaster movies. I said, this is the wrong time to be offering that movie to me. Okay, now of course that didn't happen, but I'm just giving you an example. Okay, so precision marketing, smart highways, precision traffic, smart cities, the list goes on and on and on. So you can look down this, predictive law enforcement I already mentioned, smart healthcare. which is basically integrating your electronic health record, as we now call it, across all different places where you've ever received health care or health diagnostics or health medications or whatever, putting all that one unified 360 view together. So what is this 360 view? Again, that's big data, is everything quantified and tracked. The 360 view, knowing my life history, my healthcare history, my personal preferences, whether I'm in a marketing situation or I'm in a healthcare situation or I'm in a learning environment, knowing all of that about me enables better delivery, more precise, personalized delivery. So all this goes right on down the line, including the little fintech example out there, where we can do sort of predictive modeling, better fraud detection, risk modeling. So now when we have more data points, so someone was saying this earlier today, is that we can do better when we have more data points. And so what I'm thinking to myself is it's not so much the data volume, it's the data breadth. Okay, so when we talk about big data, people always like to think about the word big meaning depth, but I think about it as breadth. Okay, having lots of data is not what makes it interesting. Having many different attributes for each item in your data set makes it interesting. So having hundreds of different features about each customer makes it interesting. Okay, so if you have, let's just pick a number, which I remember from my HP 25 calculator days. Anyone ever use a calculator like that? Not too many people in the room. Okay, so it had a nice little factorial function. You know what a factorial is, right? Okay, so any number is a factorial is itself times the number less than itself times the number less than itself. Okay, so 3 factorials, 3 times 2 times 1. 4 factorials, 4 times 3 times 2 times 1. All right, so it's basically the number of combinations you can generate from n things. Okay, so if I have 3 things, I can take things 3 at a time, 2 at a time, 1 at a time, and there's 3 times 2 times 1. There's 6 ways to do that. All right, so if you have 65 things, like I say, products you want to offer to different customers, and of course your customers are all different. They're all personal individuals. They all have their own preferences, intents, stages of life, things that they want to buy, things they're not interested in. And so how many different combinations of 65 different things? If your store has only 65 different things, I guarantee you are a small store. Most stores have millions of products, right? But let's just say you have a very small store, so a little kiosk at the airport, you have 65 things, all right? So if you want to offer different individualized combinations of 65 things to the number of customers, how many unique combinations, that is, how many unique customers could you serve? Well, 65 factorial is a number larger than my calculator can produce on the screen. It's bigger than 10 to the 99. There are more than 10 to the 99. Oh, by the way, 10 to the 100th is a Google, not the search engine Google, but the number Google. Okay, there's more than 10 to the 100 combinations of just 65 things. All right, so if all I have is 2 pieces of information about my customers, I'm not learning much. But as soon as I have 65 pieces of information, now I can serve not only this Earth, but all the Earths that are out there of customers. All right, so precision and personalization, to me, is sort of like the summary of what data science does for every part of our lives. Okay, so I call this the XYZ of data science. It's where X, Y, and Z are anything: healthcare, medicine, learning, marketing. Smart X, precision Y, personalized Z. So this is how we're seeing this manifest in our day-to-day lives and in our work. So what is this data science? And people say, okay, that's just fine to talk about this, but what are you doing? So for me, I like to put it really simple. Okay, I always talk about the best things to do in data science are usually the simplest things. All right, so why do I say that? Well, people may have heard of the Netflix prize. So Netflix offered $1 million for an improvement by 10% on their movie recommendation engine. So if someone could come up with an algorithm that had a better than 10% success rate of people actually renting the movie after seeing the recommended product, it was worth $1 million to give a prize for that. And so the team that won that Netflix prize, they actually did achieve the goal. Their algorithm was never implemented by Netflix. Netflix paid $1 million for this solution, and they never implemented it. Why? Well, if you look at the published paper, which all these competitions require the winners to publish their algorithms, the published paper had the mathematical algorithm, which was a 50-page algorithm. No way any company is going to implement a 50-page mathematical equation as the core operating algorithm of their business. I mean, it's fragile, it's sensitive to the modeling errors, it's sensitive to the types of data. I mean, that's like, no way we're gonna go down this path. So they paid the prize money, but they never implemented it. So I say, let's go back to some sort of simple, basic things we're doing with our data. We're discovering new categories, new classes of behavior, new classes of customer, new classes and categories of events. And not only do we discover those things, we discover what distinguishes them. Okay, so a little cartoon, as you see in the graph there, and my astronomy colleagues and I, we call that the banana diagram. So you see the banana at the center. So this is class discovery. You discover 3 classes of objects in this synthetic data space. Okay, so we have 3 classes. We have a peanut, a banana, and a potato. Okay, but not only do you discover these 3 categories, but you find out what makes them different. What are the characteristic values of P1, P2, and P3, which are just random data? This is toy data. What are the values that make a potato different from a peanut or different from a banana? So once you learn those boundaries, for example, if you're learning different customer segments or different cyber event data, cyber event categories in your data, you can now distinguish one thing from another by understanding what's the boundary between the different categories. So class discovery, discovering the categories, and then also discovering what distinguishes them. That's straightforward stuff, needs to be done. Correlation discovery. So what's correlation discovery? It's finding the patterns and the trends in your data. So whether it's a principal component analysis or something else, you're finding the patterns and trends in your data. From what guess what you can do? You can build a predictive model. When you know that there's a certain dependency of these variables on these other variables, you can build a predictive model. So I prefer to call that predictive power discovery. Okay, so you're now able to predict something because you discovered this correlation, this pattern in your data, this trend in your data. Then there's the third one listed here, is actually a category which you'll never find in the statistics book, surprise discovery or novelty discovery. If you look in the statistics books, the closest thing that this comes to is outlier detection. But outlier detection sounds so negative. Okay. When I was growing up, outliers were the things you expunged from your data set. You found an outlier, you deleted it. That's bad data. Okay. And I'm thinking to myself, what did I do all those years? Because for me, this is the most exciting part of data science, is finding the unknown, the surprising, unexpected thing. If you go off and delete all your outliers, you might be throwing away gold. Don't do that, okay? Keep the most interesting, surprising thing, the thing that doesn't fit your model. All right? I love the data points that don't fit my model because there's great discovery potential there, okay? So this is simple stuff, right? So get your statistics book out that tells you how to do outlier detection and throw away the last few paragraphs of that chapter that says, okay, now you can throw those away because you've just cleaned your dirty data, and throw that away and say, now analyze these data because your Nobel Prize might be waiting. Okay, this is where discovery will happen. And then sort of slightly different, that doesn't quite fit the little banana diagram there, is link discovery or correlation discovery, which is finding these unusual compact networks within your data set. So people often ask me, what's the future of data science? The future of data science is graph analytics. Everything is a graph. Get over it. The whole world is connected. You're connected. Your things are connected. Your product space is connected. Everything has a relationship between itself. For example, in a product space, similarity of different products or products that sell together. So you probably heard of the famous beer and diapers example in data mining textbooks. There's also another one which showed that people like to buy strawberry Pop-Tarts before natural disasters. Okay, so everything is connected. You and me and things. Okay, so learning graph analytics is your future. Okay, so the graph analytics is really very different from standard sort of Euclidean stuff, which is why I can't really draw it on a map like the one shown at the banana diagram. So let me give you an example of how a metric in a link analysis will not behave at all like in a Euclidean space. Okay, so if you're creating a similarity metric between different customers or between different events or different things in space, you can create a distance metric. Familiar with distance metrics, I'm sure? Okay, so a lot of distance metrics have to follow certain rules. That is, distance has to be greater than 0, unless you're comparing A against itself. So the distance between product A and customer A and customer A has to be 0. The distance between customer A and any other customer has to be greater than equal to 0. All right, those are some very basic rules. There's other rules that said the distance from A to B is the distance from B to A. Those are simple rules. We also sort of unknowingly sometimes impose a triangle inequality. Okay, so the distance from A to B plus the distance from B to C is greater than, or A to C. Right? The triangle inequality says the distance of A to C, the hypotenuse, is less than or equal to the sum of the two sides. That's not true in a link analysis space. That isn't true at all. And so I actually have one of my grad students who's still working on his dissertation, though I left the university 6 months ago. He's doing this kind of what's called a semi-metric space, looking through the medical research literature to find journal articles that have the following property. Okay, so I'm going to give you the simple version, but he's looking at a more complex version of the following simple statement. Imagine you're trying to find a cure for cancer in existing research articles that might already be there and no one ever realized, because there's so many different journals in medicine that there's not a lot of crosstalk and communication between those communities. And so you find some journal article in this journal that overlaps 50% in its content with an article in some other journal. All right? And so this might have some kind of treatments for certain kinds of diseases. This might be sort of side effects of certain drugs. And then there's another journal over here that talks about drugs that treat cancer. All right? So the overlap between article A and B is 50%. The overlap between B and C is 50%. The overlap between A and C is 0%. Convert that similarity into a distance metric, it says the distance from A to B is 0.5, the distance from B to C is 0.5. So by triangle inequality, the distance A to C must be less than or equal to 1, right? Well, in this case, the distance from A to C is infinity, 1 over 0, because there's 0 similarity between the two documents. You would never discover that if you were just looking at distance from A to C. You would, because they were infinitely far apart. Why would I look at two things that are infinitely far apart in my space? All right, so you need some completely different way of thinking about your data, and graph analytics and link analysis gives you that different way of thinking. So to me, this is a simple summary of the things you can do with data that aren't complicated. I don't need to stand up here and give you a lecture on SVMs and latent Dirichlet allocation and all kinds of cool stuff, some of which I can pronounce, but we can do straightforward things. So when I say all the world is a graph, I'm not kidding you. So the Internet of Things we've talked about is really an Internet of connected things. Everything is going to be connected. And once we have this Internet of connected things, and it's primarily in a geospatial, temporal, changing world, that is, things are moving through space and time, we now need to do modeling on this dynamic world in order to understand what's going on around us. So that's what we want to try to achieve with this Internet of Everything, is understanding highways and cities and buildings and you and me and healthcare and education and cars and air travel, such as it is, and so on. So what we're trying to achieve, the big challenge that we're trying to achieve from all of this, is this sort of real-time, and real-time in quotes, because real-time doesn't necessarily mean like that, but it means faster. I think we heard something earlier today where something that I think Jeremy was telling us that it used to take like 30 days for their business to do, they can now do it in 3 seconds. Okay, so that's real time. Okay, if you can do something that used to take you 30 days and you can do it, in less time than it takes you to get a cup of coffee, that's real time. So I read a blog article recently that said advanced data analytics basically means the end of the coffee break, right? Because the answer comes back before you have time to go get the coffee and come back. It used to be, I remember those days, I'd set some program running and I'd have time to go get have a break before the thing finished, but not anymore. Okay, so we want to do real-time analytics, and real-time in quotes again, real-time analytics from streaming data, because our world is everything quantified and tracked, to derive actionable intelligence from that, okay, to make decisions, okay? And so web analytics example, in the middle of the slide there, talks about, looking at the click stream of your customers to know precisely at that point in time what might they be interested in. Or looking at the click stream of the one we heard about today, healthcare patients who are looking for information on a healthcare website about maybe a condition or treatment or trying to take care of some health issue, understanding by that click stream what they're really looking for and making recommended products In this case, products aren't like Amazon products. They might be, here's the doctor you need to see, here's the medical white paper or FAQ you need to look at, or here's the facility that you need to go visit, or something. But anyway, giving some actionable intelligence off of the clickstream. And so we can see this kind of thing happening anywhere and everywhere. This little list here is not meant to be comprehensive, again, because everything in our world is quantified and tracked. So health alerts, tsunami alerts, cybersecurity alerts, social event alerts, preventive fraud alerts, predictive maintenance alerts, infrastructure monitoring, all these things businesses are doing nowadays, and more. Putting those little beacons, which I like to call sentinels, monitoring the data stream to say, hey, something is happening here. Okay, what's a sentinel? A sentinel is the guard up on the gate that says, hey, the enemy's coming. Wake up, everyone. Okay, so the sentinel is the one that gives the alert based upon the data. So the data is, oh, here comes the enemy. The response is to not say, oh, okay, I see that the enemy is coming. Let me have a cup of coffee now. No, it is to alert the troops to get up and defend the castle. Okay, so action needs to be taken from these alerts. Of course, some of the alerts are just informational. They're not alerts anymore. They're just informational messages, but some really are actionable or need action. Okay, so that's what we're trying to achieve, is that implementation of a sentinel-type functionality, which is what the data science and machine learning algorithms get us. So we impose that machine learning, those four things I just showed you in the last slide, link discovery, correlation discovery, so on and so on. We implement those discovery mechanisms in our data stream and say, hey, I found one of these things, go out and take action on it. All right, so sometimes those actions will be productive, sometimes they won't. Sometimes this is achievable, sometimes it's too expensive. So there's a lot of risk going on here, right? So for some of the businesses that I've been talking with since I left the university, now I'm in the role of basically a data science evangelist for my company. I go in and talk to potential clients, and they're getting the message that they need to invest a lot of money for some of this stuff. And that's true. You're going to probably need to invest in hardware, software, and personnel solutions. So that's a risk for those organizations to make that investment. But there's, as we heard a lot of already this week, and certainly from Jeremy's talk this morning, there was tons of examples of the rewards to come and cost savings and so on. So we're trying to achieve value from all of this. And I like to use little simple ways of remembering things. So I call these my 3 D to Ds, okay? The 3 ways you derive value from your data. So there's data to discovery, data to decisions, and data to dollars, or if you want, data to dividends, okay? So how do you discover new knowledge? How do you improve decision making? And how do you actually innovate to get return on that investment, or in this case, return on innovation? So I'm going to give you 3 examples of those. My clock is ticking down. You won't actually throw me off the stage in 2 minutes, will you? Oh my gosh, okay. Clear my breath, and here we go. Okay, so 3 case studies, which I won't go into much depth here because of the time limit, but these are metaphors of the things I just talked about. I can clearly talk more about them than I'm going to have time for. So there's an astronomy example. Again, this is not an astronomy lesson, but this is an example of knowledge discovery from data. So we're building this huge telescope in South America. It's going to produce an image of the sky every night for 10 years. So we call that cosmic cinematography. So after 10 years, we're going to have a 200 petabyte archive, but that's going to be on. So this project will end about 15, 16 years from now, because it's still being built. It won't start working until 6 years from now. Then it's a 10-year project. So 16 years from now, 200 petabytes will fit on your thumb drive. And if you don't believe me, I just saw a half terabyte thumb drive for about $60. 512 gigabyte thumb drive for like 60. Yeah, it's scary. Anyway, so what's scary about this project is that it's going to produce, for each object in the sky, of which we're going to have 50 billion objects, it's going to produce 200,000 attributes for each of those 50 billion objects. So the number of possible combinations of interesting astronomical things we can explore is 200,000 factorial, which is a 1 followed by more zeros than I could ever possibly imagine. Okay, so if 65 factorial is 10 to the 100, I don't even want to think about what 200,000 factorial is. So the number of combinations of interesting things we can explore is enormous. So the breadth of the data, not the depth of the data, is the big data challenge for us. And I think that's true for all of us, that big data variety. We have so many features that we've tracked. So there's lots of stories about that. Again, for lack of time, I'm not going to give you all the lovely stories I'd love to tell you. The second example are Mars rovers. Again, this is not an astronomy lesson. This is a metaphor for a business case you might have. So this is an example of data to decisions. So what's the Mars rover? It's this little thing that roves around on the planet Mars, which is out there, and there's no humans involved. It's an autonomous system collecting data and doing real-time intelligence gathering to make real-time decisions. So that might be like real-time bidding on micro bidding on ad placement on websites. It might be other kinds of things. So a real-time action requires real-time algorithms, which means basically Sentinels, that is, those machine learning algorithms helping to make those decisions possible. Now, of course, not all decisions should be done autonomously. I understand that, and there still needs to be humans in the loop. I absolutely agree with that statement. But there's some things you can put into that pipeline and say, I'm going to set up algorithms to, when I see this type of thing happen, take this action. Okay, so our little Mars rover, when I see these kinds of rocks, keep going. Or if I see a trend towards this direction, looks like there's more chances of finding water or finding titanium or whatever I'm looking for on Mars, go that way. So follow your data, follow the leads, follow the trends, follow the line that leads to greater discovery. And the last one is digital marketing analytics, which is basically what we've already been talking about, which is you're collecting all this data about your customers. You can innovate all kinds of data products, all kinds of sort of data monetization aspects. That's a loaded word, I understand, but basically trying to derive business value from all that data coming from many different sources in your marketing environment. Okay, so delivering the right product to the right customer at the right time. Okay, so there's a lot of words about that, and I'll just move on to the last couple slides, then I'm done. So there's an architecture for this, which actually has existed for quite a number of years, and no one really paid too much attention for it, but I really love it because it's the core of it is machine learning. The core of it is data science. Okay, long before there was such a thing as data science, the U.S. Air Force had a research program where they solicited research proposals for data-driven, dynamic data-driven application systems. Okay, so you take a measurement, you make measurements, you apply some inference on that to learn a model, then you predict from that model that something's going to happen based upon the model you learned from the measurements, and then you take action. That's the steering. So steering means steering your resources, which might be people, or it might be, customer ads. It might be anything. Okay, you're emergency responders. You're steering a resource in response to what you've learned from your model. So measurement, inference, prediction, steering is the model, the architecture for this. The core is the INP part, inference and prediction. That's the machine learning. So we all live in this space. That's what's so exciting about IoT, about fintech, about big data, about all the stuff we're talking here this week. So there's lots of applications listed in the middle of that slide there. But it's all about getting really good models of how the world works, whatever your world is, and responding to that in informative and actionable ways. And so I like to say it's all about going from sensors, which is the measurement, to Sentinels, which is the machine learning data science, to making sense of it all. Okay, so the sequence actually has a fourth step. From sensors to Sentinels to sense making, to dollars and cents making. Okay, so from sensors to Sentinels to sense making to sense making. And I'm out of breath now because I've been rapidly talking. So that's what we're trying to achieve, this value chain in our business. And again, I don't want to focus on monetary value. Whatever value is in your organization, saving lives or whatever it is, deriving value by understanding how your world works, collecting that information and data, that big data that's tracking and monitoring your space and your world, and making better decisions from it. That's what we're here for. So making the long story short, to derive value across all these different disciplines requires learning from data, and there's those 4 steps in data science to achieving these 3 D to Ds of business value. So thank you very much.
Thank you so much, Kirk.